Begin with a clear sky and a patient camera. The Milky Way hangs like a dim river above a silent field, and the only sound is the soft click every few seconds as the mount nudges the stars back to center. A compass on the ground vibrates. A small arrow hunting north while constellations slide. A handheld radio whispers between stations, as if the air itself were crawling. Nothing else moves. Not the fence posts or the grass or your breath. And yet the dome above is not fixed. Our senses say stillness. Our instruments refuse to agree. Aim the lens at Polaris and let the shutter stay open. The star is supposed to be a hinge, yet the photo returns with a tiny arc, a reminder that even the hinge belongs to a larger wheel. A gyroscope on the table resists your hand, fighting for its axis while the sky wheels overhead. The paradox bites here. We trust our seat on Earth more than the numbers coming from sensors and pixel arrays. Which one deserves the name of rest? What would it take to prove that our peace is a kind of drift? If stillness is only an opinion, where is everything going? You can feel the stack of motions piling up under your shoes. The floor turns with the planet. The planet loops the star. The star sweeps a path inside a spinning disk of other stars and cold gas. That disk glides among neighbors like a city block carried by a broader flow. None of those layers announce themselves to your inner ear. They reveal themselves as tiny shifts in star positions over the years, as slight squeezes and stretches in spectral lines, as a lopsided glow in the microwave background that leans a certain way on the sky. The truest calm in nature is not the quiet we feel, but the agreement between devices that do not care where we stand. Place a prism in front of a starlight beam, and you meet the wind of space. Color splits, and inside those bands, a narrow notch slides a hair to the blue or the red. That slide is motion recorded in light. The thumbprint of an element rides along the flow and tells you that a star runs a little toward us or away from us. Gather many thumbprints from thousands of stars, and a pattern begins to rise out of the noise. The pattern says, "Our home moves." It sets a scale for speed and offers a heading. The heading is not a sign on a road. It is a vector drawn on a sphere that holds everything you will ever see. Look at the numbers long enough and the world becomes stranger. The planet jitters your instrument a little each year, a small loop on a plot that repeats with the seasons. The sun leans into a slow drift among nearby stars. The galaxy carries us on a long turn that takes hundreds of millions of years. Far beyond that turn, great swaths of galaxies share a preferred direction, like leaves sliding along a gradient you cannot feel. None of these flows ruffle your hair. They live in long baselines, in surveys spread across deserts and mountaintops, in dishes that listen to hydrogen whispering behind curtains of dust. When we put the maps together, the calm night cracks open. Stillness dissolves into motion, layered upon motion. Return to the field. The camera finishes its exposure and the star trails resolve into clean arcs. You zoom and pick a bright star. It betrays a tiny oval of motion, proof that our mount is not perfect and neither is our trust. On the compass, the needle seems steady, but next to it, the phone accelerometer says we are turning. A human is unbearably local. We are bound to the bench seat of our favorite frame, and we accept its verdict without appeal. The devices have no loyalty. They report what the sky imprints upon them. In their quiet, they become judges, whose sentences add up to one claim. There is no final rest. Only the right frame makes order out of drift. Try a human scale test. Sit in a train with the curtains drawn. When the platform begins to move in the opposite direction, your stomach tells a lie that your carriage has stayed put. Lift the curtain and perspective corrects you. The cosmos offers no curtains to lift. Only measurements that behave like careful hands on a fabric we cannot see. A dipole in the microwave glow points a direction. Splitting of distant light records relative motion. The tiny yearly wiggle of nearby stars reveals neighborhood dynamics. None of them alone persuades the heart. Together they become hard to deny. This is where the question lands. If motion is layered and no single frame can claim authority, What counts as a destination? If we cannot feel the current, how do we map it? If our galaxy is one eddy in a larger river, does the river itself have banks, a gradient, a fall line? Are we falling towards something, or are we sliding away from something else? Why should it matter to anyone who will still make breakfast and head to work in the morning? It matters because navigation shapes meaning. A species that learns it is adrift makes different choices than a species that believes it is anchored. If the current is strong, we will never see certain lights again as the universe expands faster than our signals can chase them. If the current is converging, our future sky will be sculpted by meetings and reshaping rather than separation. On the scale of families, this seems remote. On the scale of time and story, it is a compass. We count ourselves by horizons. Change the horizon. Change the story we tell about time. Let your eyes adapt and sweep the faint band again. Notice dark threads crossing the river. Those are dust lanes that hide newborn stars. Notice bright knots along the band. Those are nurseries where gas turns to light. The texture is not decoration. It is a field of evidence. The rotation of the disk, the tug of the center, the push and pull of neighbors, all leave fingerprints in that texture. You will not solve them by looking, but you can plan to follow the numbers where they lead. The quietest nights teach the fastest truths because they let small signals stand up out of noise. Now listen with a different ear. A radio dish points not at a bright star, but at a lane of darkness. The darkness is full of a single note from cold hydrogen filling the disk. It is not a bell. It is more like an electrical hum under the world. As the dish sweeps the plane, the pitch bends a little. Each bend marks motion. Draw the bends across the sky and they become a ledger. Read the ledger and a map appears. The map does not say we drift aimlessly. It says our path has a bearing inside a larger circulation. Bring it closer again. Lift a spinning bicycle wheel by its axle and try to twist it. It fights you with stubborn grace. That small fight is a home-scale echo of a giant truth. Angular momentum keeps systems organized while they exchange energy and rearrange. Our star, its planets, the star city that holds them, all keep this habit. Organization does not mean permanence. It means predictable change. Predictable change allows projection. Projection lets us guess not only where we have been, but where the flow prefers to go. Think of it like this. A river does not ask you to feel water to know direction. You read the white lines of foam and the slow tilt of the surface around stones. The universe has its own foam lines. They are built from statistics of motion and light. They point, faintly, but consistently, toward a broader contour that we will spend the rest of this film mapping. The method is simple to say, and hard to do. We will compare frames, test devices against one another, and keep only the headings that survive. The goal is clear. Build a picture that begins with a backyard mount and ends with a chart of the basin that carries whole clusters of galaxies. To stay honest, we will carry two scales at once. The first is the scale of one person with ordinary tools. A single image, a single dial, a single notch on a spectrum can make a claim you can test on the next clear night. The second is the scale of a civilization. Millions of such claims, pooled and cleaned, reveal a tendency that no eye can feel. If there is a heading, it should appear on both scales in ways that fit each. If no coherent heading appears, our urge to see patterns must yield, and we must say so. That is the bargain of evidence. The plan must also respect doubt. Some flows are stable, others are only suggested by incomplete data. Some vectors sharpen when a new survey arrives. Others fade. We will keep a running line between what is secure and what is proposed, and we will make that line visible at each step. If the line moves, we will move with it. Our aim is not a slogan. Our aim is a measured story. Picture the years like stacked negatives from a film camera. Each frame looks nearly the same. Stars keep their distance, the band keeps its tilt, the field keeps its quiet. Only when you lay the frames down together and align them does motion appear as a faint crawl along the edges. That is how we will work. Align the frames. Subtract what belongs to us. See what remains. Call what remains the current. Why begin at the smallest scale rather than jump to cosmic claims? Because the smallest scale keeps us honest. Your bench test of a gyroscope does not care about fashion. Your lens does not salute a theory. Your radio does not attend conferences. These tools either agree or they do not. When they do, the agreement has a quality that endures. When they do not, new work begins. The river we hope to map will demand that kind of patience. There is also a cost to ignoring the current. If the universe expands in a way that isolates us over time, then the archive we build now will be the only bridge to parts of the sky that later generations will never measure directly. If large masses shape our motion, then understanding them will refine our estimates of long-term encounters. If empty regions steer paths by absence as surely as masses steer by presence, then what looks like nothing may be part of the compass itself. These are not ornaments on a cosmic story. They change what future maps can be. As the night deepens, the meadow grows colder, and your breath turns to a pale cloud in the headlamp beam. You check the mount and watch a graph rise slowly on a small screen. A plot of drift error against time. You delete a bad frame, adjust balance, and wait again. The patience is part of the craft. It keeps a human being inside a web of devices that would otherwise run alone. It reminds you that a measurement is a conversation between matter and method, not an oracle handed down. We are nearly ready to trade pictures for maps. We will step from what the eye can gather to what careful statistics reveal. We will allow a mundane fact to lead the way. Every claim about direction depends on a frame. Choose the wrong frame and lines that should be straight appear curved. Choose the right frame and curves flatten into something you can model and test. Frames within frames give us the ladder we need, and each rung will carry a proof of its own. One more look at the sky. The river fades toward the west. A satellite cuts a neat line through the exposure, a reminder that some motions are close enough to feel if you had walked a little faster and looked up at the right second. Most motions are not like that. Most live below sensation and above comfort. These are the ones worth chasing, because they teach us how to tell the world that our lives are tiny boats on a large water, and that does not make them small. It makes them navigable. We will begin our chase with the smallest piece of drift that we can measure clearly, the motion of our own star among its neighbors. If we can remove our local spin and orbit to see that motion cleanly, we earn the right to climb to the next scale. If we fail, the ladder breaks, and the larger map is not ours to claim. It is a severe bargain, but it is fair. And it is the only way a backyard tripod and a mountain observatory can speak the same language. If this helped clarify the cosmos, please like and subscribe to the Quiet Universe channel. Now we test frames within frames, starting with the drift of our own star. A photograph freezes a moment, but the universe refuses to stand still long enough for any frame to hold it. When we speak of a frame of reference, we imagine something stable, a grid nailed into the void. In truth, each frame is drifting through another, carrying its own illusions of rest. The first rule of cosmic motion is that there is no privileged seat. Every observer, from a mountain observatory to a spacecraft, is falling somewhere, and the art lies in subtracting one motion to see the next. Start small, with the rotation that defines our days. A pendulum in a quiet hall does not trace the same path hour after hour. Its swing drifts, carving a slow star on the floor. The pattern is the signature of a spinning planet. The floor itself is moving, dragging the pendulum's base beneath the swinging weight. The pendulum becomes a witness, impartial, revealing the truth that our most reliable reference, the ground underfoot, is turning through space. That single fact forces a question we rarely ask if the ground moves. What stays still enough to measure it? The early astronomers answered by stacking reference points. They treated the stars as nails fixed in a perfect dome. For centuries, that trick worked, but telescopes ruined the illusion. The stars, when measured over decades, creep. The dome fractures into layers, each moving according to its own pattern. A framework that once looked eternal dissolves into slow rivers of light. Each new instrument exposed the old one's bias, showing how every definition of stillness is a local convenience. When the frame shifts, the story shifts with it. The ancients drew their maps with Earth at the center and were content. The planets wandered in odd loops, but those loops could be patched with circles upon circles. Then came a simpler frame, centered on the sun. The loops straightened into ovals. The math grew cleaner, and a new order emerged. What changed was not the planets, only the observer's seat. It was an act of humility disguised as progress, the admission that the sky's complexity was our own perspective bending back on us. We repeat that act every time we advance a layer. Today's scientists trace the sun's motion against nearby stars, only to learn that those stars have their own currents. They use the galaxy as a frame, until data from radio telescopes show the galaxy itself sliding within a greater tide. Even the cosmic background, the oldest light we know, is not a fixed canvas. It carries a faint dipole, a pattern that tells us our entire system is moving relative to that ancient glow. The lesson echoes again no matter how wide the net. The universe always slips a layer deeper. Imagine standing on a slow conveyor belt that rests upon another belt and another beyond sight. Each belt moves at its own pace, and for a moment, they may align so the motion cancels, tricking you into thinking you are still. The illusion holds until one belt speeds up or slows down, and then the whole pattern stirs again. That is what a frame of reference really is. A temporary piece between moving parts. We are fortunate that the mathematics allows us to describe it at all. Now consider the instruments that reveal these hidden motions. A gyroscope resists change. It holds direction while its base turns. An accelerometer measures every subtle push. A spectrograph reads the color shifts of light from distant stars. Together, they become translators between frames. Each device occupies a layer of motion and reports on the one beneath. To interpret their signals is to peel away these layers until we see the common drift that threads them all. In everyday language, a frame of reference is the perspective from which motion is judged. On Earth, we call a ball tossed into the air an arc. From a plane passing overhead, the same ball traces a wavy line. From the sun's vantage, it draws a complex loop, riding a planet that itself swings around a star. Each story is true inside its own frame, yet each is incomplete. Truth in physics is less about declaring which frame is right and more about learning how to translate between them. This translation is what gives modern cosmology its power. To understand the Milky Way's rotation, we must first remove the motion of our own star around its local group of neighbors. To understand that group, we must subtract the pull of the galactic center. To interpret the galaxy's flight among others, we must measure our speed against the glow of the background itself. Each subtraction removes a mask. Each mask hides a deeper truth. The process is both mathematical and philosophical, a repeated admission that what we see is shaped by where we stand. One might ask why this layered approach matters to ordinary life. The answer lies in perception. Our minds crave anchors. We build meaning on fixed points. But in a universe without stillness, stability is a construct. The practical gift of understanding frames is not abstract. It protects us from confusing our comfort with reality. It reminds us that models are tools, not verdicts. A compass that knows it drifts can still lead you home. The quest for a universal frame continues, but the evidence suggests there is none. Einstein formalized this intuition, showing that motion and rest are relative concepts. Even time itself bends to the frame that observes it. Two clocks in motion with respect to each other do not agree. Not because one fails, but because nature refuses to privilege a single rhythm. The realization shattered the dream of a fixed backdrop and replaced it with something subtler: consistency across translation. The laws of physics hold true in every frame. even when the measurements change. Such invariance is the quiet heart of the cosmos. It allows galaxies, atoms, and observers to share one grammar. Without it, no communication between frames would be possible. When scientists compare data from satellites and ground stations, they are performing that act of translation, making sure the grammar remains intact as each instrument speaks from its own drifting seat. It is a ritual of calibration, and it binds our local understanding to the wider flow. Picture a spacecraft leaving Earth, its engines cutting off as it enters freefall. Inside, an astronaut releases a tool and watches it float. To her, the tool is motionless, sharing her frame. To us, on the planet below, both are hurtling thousands of meters per second along the orbital path. Who is right? Both, depending on the question. The paradox only dissolves when we recognize that motion has no meaning without the context of another object to compare against. In this way, a frame of reference is not merely a coordinate system. It is an agreement among observers about what counts as rest. The stronger our measurements, the more these agreements must adapt. In the coming chapters, we will watch how this principle scales from local tests to galactic cartography. The shift from apparent simplicity to layered motion is not only a story of science, but also of perception learning its limits. Think of the cosmos as a hall of mirrors, each mirror moving slowly within the next. The reflections repeat but never quite align. Sometimes they reinforce each other, producing the illusion of stillness. Sometimes they slip out of phase and reveal motion at every level. We live in that shifting reflection, tasked with deciding which image to trust for navigation. Each mirror we clean shows a deeper set of motions, and each new layer of clarity expands the puzzle rather than closes it. The pendulum's drift, the wobble of planets, the trembling of light from distant stars. All of these are notes in the same song. They remind us that our sense of rest is provisional. The beauty of this realization is not that it denies peace, but that it reframes it. Rest becomes a relationship, not a state. It is the moment when our motion matches the motion of the frame we choose to inhabit. In that instant, everything appears calm, even though the current below never stops. To navigate the vast system of nested frames, we must accept uncertainty as a companion. Each correction brings us closer to the true flow. But the horizon of correction moves with us. There will always be another frame beyond our reach, a wider stage where our entire map drifts like a leaf. The humility this demands is not defeat. It is alignment with reality. We cannot freeze the universe, but we can learn to move within its grammar. So we begin our climb toward understanding motion, not as noise, but as structure. We will follow the drift of our own star among its neighbors, then expand outward to the larger turns that carry whole systems. Each layer will challenge what we call rest and reveal new scales of movement. The act of peeling away frames will turn observation into exploration, and exploration into meaning. Our next task is clear. To test the idea of frames within frames, we must measure the sun's motion through the local field of stars and compare its course with theirs, looking for the pattern that defines our immediate neighborhood. The story of motion becomes tangible only when we try to measure it. The sun, that steady disk in our sky, is not steady at all. It slides through a sea of nearby stars, pulling the planets in a long, invisible arc. For centuries, this drift was an assumption. Today, it is a chart filled with numbers precise enough to draw a path across millions of years. Measuring the sun's motion means learning to listen to the faint shuffles of the stars that surround us and translating them into the rhythm of our own journey. Begin with the simplest test. Pick a nearby star and record its position tonight. Wait a year, then record it again. The change is minuscule, a fraction of a degree, but it is real. This tiny shift, known as proper motion, was one of the first signs that the sky is alive. When the first catalogs of proper motions were compared, a pattern emerged. Most stars moved in scattered directions, but a few shared a common bias. The bias pointed toward a particular constellation. That direction became a clue to the sun's drift, suggesting that we are gliding through our neighborhood toward a region of the sky, while stars behind us seem to open outward. Every motion has two parts. One is the sideways drift. The other is motion along the line of sight. The sideways drift reveals itself through angles, but the in or out motion reveals itself through color. When starlight is spread into a spectrum, its familiar lines are displaced slightly toward the red or the blue. A blue shift means approach. A red shift means retreat. Measure many stars and plot these shifts. And a pattern takes shape like the wake behind a slow ship. That wake is ours. The Sun, with its planets, sails at about 200 kilometers per second around the galactic center, and roughly 20 toward a point near the constellation Hercules. To us, that number sounds immense. Yet compared with the scale of the galaxy, it is a patient crawl. The difficulty lies not in detecting motion, but in trusting what the instruments say. A telescope on Earth moves with the planet. A spectrograph on a satellite moves with its orbit. Even the signal itself passes through moving gas and a turning atmosphere. The scientist's task is to peel these motions away, one after another, until only the drift of the Sun remains. It is a layered subtraction, like removing successive veils of wind until the quiet underneath becomes audible. One way to find that quiet is through long baseline interferometry, a method that links antennas separated by continents. By timing the arrival of a signal from a distant quasar at each station, we can pin down our planet's position in space with astonishing precision. Each slight change in delay reveals how Earth's orbit, rotation, and even tectonic shifts alter our frame. Once those local effects are removed, the residual motion describes the path of our solar system through the galaxy. The Sun's course becomes not a guess, but a measured line against the backdrop of the universe itself. Simply put, measuring the Sun's drift means defining stillness first. There is no absolute yardstick, only agreements. Astronomers use the local standard of rest, an average motion of nearby stars that forms a kind of floating reference grid. Against that grid, the Sun is not still, but slides slightly ahead, like a runner gaining slowly on a moving crowd. This subtle lead produces a continuous change in which stars we call near, over thousands of years. Constellations warp, alignments fade, and the night sky's geometry evolves. What we treat as eternal artwork is, in fact, a dynamic pattern painted on flowing canvas. Why it matters is simple. To know our direction is to predict encounters. The solar system is not fixed within empty space, but travels through regions of gas and dust that vary in density. In distant epochs, those passages may have influenced the influx of comets or even the climate on early Earth. Motion through space is also motion through environment. The stars are not only lights, they are markers of a cosmic weather pattern that shapes the long fate of worlds. Imagine standing on a platform as a train departs. The station seems to slide away, yet it is your frame that changes. The stars perform a similar trick. Those ahead seem to approach, those behind to recede. When plotted carefully, their motions form a dipole, a pattern that points back to our direction of travel. The first astronomers who saw this pattern must have felt a quiet awe, realizing that humanity's home star was part of a current much larger than any myth had imagined. The instruments that refine this picture are more complex now, but the idea remains the same. The Gaia satellite maps positions and motions of more than 1 billion stars with such accuracy that even their subtle shivers become data. Each dot in its map is a vector, a line showing speed and direction. When these lines are averaged, they reveal the solar system's course with clarity that was once impossible. Gaia's precision is high enough that the Sun's slow oscillation above and below the galactic plane can be traced, a gentle bobbing like a swimmer moving through waves. The frequency of that motion, roughly once every 30 million years, hints at cycles that may influence comet paths and perhaps even geological rhythms on Earth. At its core, the measurement of drift is an act of comparison. To detect our own motion, we must see the background shift. If the background itself is moving, the task becomes recursive. Each correction forces a new frame, and each frame reveals new structure. The search for absolute rest ends in a realization both humbling and liberating. The only absolute is change itself. Every coordinate we draw is a snapshot of a dance that never stops. There is also an emotional current running beneath the numbers. The sun's path through space is a quiet reminder that permanence is an illusion. The same star that rises each morning is changing its neighborhood year by year. 1,000,000 years from now, the familiar constellations will be unrecognizable. The North Star will no longer be our pole. Future observers will live beneath new patterns of light and shadow. Our descendants will navigate by maps we cannot imagine, their skies shaped by a motion we began to measure in faint shifts and patient graphs. At this point, one might ask whether it truly matters to know such motions. After all, the planets still orbit, the seasons still turn, and life continues without caring about our galactic drift. But knowledge reshapes perspective. To realize that our star has a trajectory transforms the night from a ceiling into a road. The very concept of rest dissolves, replaced by the idea of participation in a cosmic flow. The data become poetry when you remember that each photon of starlight we catch carries not just color but direction, the whisper of the current that moves us all. Think of the instruments scattered across the Earth and in orbit, each one a patient listener. Radio dishes follow hydrogen lines that tell of rotation. Spectrographs record shifts in color. Spacecraft carry atomic clocks that compare frequencies with masers on the ground, searching for the slight differences that betray motion. The entire network behaves like a single vast sense organ, mapping the galaxy's tide by measuring how every wavelength leans. If we plot all this data on a single sphere, patterns emerge. One hemisphere glows with stars slightly bluer, the other slightly redder. This gradient is not an illusion of calibration. It is the Doppler imprint of our motion through space. It is the celestial equivalent of wind on the skin. We do not feel it directly, yet its evidence touches every photon we receive. Even the cosmic microwave background shows the same asymmetry. A faint brightening in the direction we travel and a dimming behind. The symmetry of the universe breaks gently, revealing our drift through its ancient light. Such findings remind us that perspective is both gift and trap. From within the solar system, the sun appears central and still. From outside, it is another traveler. The difference between those views is not merely academic. It defines how we construct truth. In science as in life, we find meaning not by assuming we stand still, but by learning how our movement fits into larger patterns. The data that measure the sun's drift are lessons in humility, precise and unforgiving. There is another layer of wonder hidden in the math. Our sun's path is not a perfect circle, but a slightly warped spiral that wobbles in height and speed. This motion threads through clouds of gas and past gravitational eddies cast by other stars. Each passage leaves subtle imprints in the solar system's boundary, the region where the sun's magnetic field meets interstellar space. As the sun moves, that boundary flexes, breathing slowly like a lung. Instruments aboard Voyager spacecraft recorded these fluctuations decades after launch, proving that the flow we measure on a galactic scale has effects close enough to touch. Why it matters once more, every refined measurement we make anchors our maps of the universe. Without knowing the sun's motion, we cannot properly weigh the galaxy or interpret the faint pulls that shape its spiral arms. Each correction sharpens the larger image, transforming scattered data into a coherent current. To trace the sun's path is to begin drawing the blueprint of the cosmic city we inhabit. The sun's drift, once an idea, is now a fact measured in multiple ways. Its velocity relative to nearby stars, its oscillation about the galactic plane, and its motion through the cosmic background all agree within known limits. Agreement among methods is the hallmark of truth. The instruments differ, the errors vary, yet the story they tell aligns. It is the story of a star, a family of planets, and a cloud of dust riding together on an endless turn through space. At its simplest, the sun's drift tells us that even the center of our daily life is not central. It belongs to a greater choreography, one that defines our orientation in both space and time. Each new measurement is a conversation with that choreography, a way of saying we are listening. We are aware that our home moves, and we wish to understand where it leads. Our next step is to look deeper into the engine that drives this motion, the gravitational heart of the galaxy itself, where invisible mass shapes every orbit and decides how the stars, including our sun, maintain their paths. Every motion we have traced so far points toward a greater source, a hidden pivot around which our entire stellar city turns. The galaxy, viewed from within, offers no single clue to this center. It is like trying to find the drain of a whirlpool while floating on its surface. Yet through generations of observation, the outlines of that engine have begun to emerge, drawn from light, velocity, and shadow. To understand the Milky Way's rotation, we must look into its heart, where gravity and time weave a structure vast enough to steer billions of suns. From our vantage point, the galaxy appears as a milky band arching across the sky. In reality, it is a flattened disk, more than 100,000 light-years wide, threaded by spiral arms of dust and gas. Our sun lives about halfway out, circling the center once every 200 million years. The orbital path is not sharp but elastic, tugged by waves of mass that ripple through the disk. Measuring that orbit was one of astronomy's first great riddles. When early radio telescopes mapped the hydrogen line, they expected the outer regions to move more slowly than the inner, as planets do around a star. Instead, the curve of rotation flattened. Stars far from the center moved almost as quickly as those close in. Something unseen was holding them up. At first, the discrepancy was met with hesitation. Perhaps the data were wrong, or the distances misjudged. But as surveys grew in reach, the pattern held. The galaxy's visible matter, the glowing stars and gas, could not provide enough gravity to explain the speeds. An invisible component had to exist, a halo of mass that stretched far beyond the visible disk. This was the first whisper of dark matter on our own doorstep, a silent scaffold shaping every orbit we see. The realization shifted the problem from local mechanics to cosmic architecture. The engine of the Milky Way was no longer a single hub, but a symphony of forces anchored by a dark structure that refused to shine. To see the engine's face, we must peer toward the constellation Sagittarius, where dust thickens like fog along a road. Optical telescopes fail here. The light is absorbed and scattered. Radio waves, however, slide through, carrying messages from deep inside. When astronomers tuned their receivers to the center, they found a compact, bright source that flickered and roared in multiple wavelengths. It was too energetic to be a cluster of ordinary stars, too small to be a supernova remnant. The source, now known as Sagittarius A, became the prime suspect for the galaxy's central mass. Measurements of stars orbiting this region confirmed the suspicion. Some of them, bright blue and young, trace near perfect ellipses around an invisible point. Their speeds are astonishing, reaching thousands of kilometers per second. From these orbits, we can weigh the unseen object. The answer is staggering, about 4 million times the mass of the Sun compressed into a region smaller than our solar system. The only known configuration that fits these numbers is a supermassive black hole. The Milky Way's engine, then, is both ordinary and extraordinary, a massive object obeying gravity's laws, yet bending space so severely that light itself can be trapped within. At its core, this engine is simple. Matter falls inward, energy radiates outward. Balance emerges. Around the black hole, an accretion disk of gas and dust whirls at relativistic speeds, glowing in X-rays and radio bursts. Magnetic fields twist through the flow, shaping jets that may extend thousands of light years. The black hole itself, silent, invisible light, is revealed by what it does to everything around it. We cannot see the hole, but we can watch space curve in its vicinity. we see stars accelerate, orbits precess, and radiation pulse as particles spiral down the gravity well. Think of it like this: a city built around a power plant it cannot see. The lights flicker, the streets hum, but the plant is hidden behind a wall of smoke. Only by measuring the vibrations in the air can the citizens deduce its shape and strength. The galaxy lives by a similar logic. Every star's path is a piece of evidence. Every filament of gas a tracer of the unseen core. When we assemble the data, a coherent portrait forms. The Milky Way's rotation curve is the fingerprint of a deep gravitational design, part visible, part concealed. In everyday language, the galaxy's engine is the combined effect of everything that has weight. The stars, gas, dust, and dark matter each contribute to the pull, but their influence varies with distance. Near the center, the black hole dominates. Farther out, the distributed mass of the disk takes control. Beyond that, the halo of dark matter becomes the main force keeping the outer arms attached. This layered structure keeps the galaxy from tearing itself apart while still allowing it to evolve. The elegance of the system lies in its balance, a balance maintained across scales we can barely comprehend. The revelation of the black hole's presence brought a new question. How did such a massive object form so early in cosmic history? Some theories suggest it grew from the collapse of enormous clouds in the young universe. Others that it formed from smaller black holes merging over time. Either way, it acts as both anchor and archive. It holds the memory of everything that has fallen into it, even if that memory is encoded in event horizons and warped space-time rather than retrievable records. There is a poetic symmetry here. The same physics that keeps a planet circling a star also binds our galaxy together. Gravity is democratic. It does not care about scale. Yet when gravity becomes too strong, it hides its own workings behind horizons. The Milky Way's engine is not just a gravitational sink. It is a boundary between knowable and unknowable. What we can describe is the dance around it. What lies inside remains beyond direct reach. The Event Horizon Telescope offered a glimpse of that boundary. By combining radio dishes across the planet into one giant instrument, astronomers imaged the shadow of a black hole in another galaxy, then turned the array toward Sagittarius A. The resulting picture, a blurred ring of light surrounding a darker core, matched the predictions of general relativity. For the first time, humanity saw the outline of its own galactic heart. The image was not sharp in detail, but in meaning it was crystal clear the equations work. Space behaves as the theory demands, even at the threshold where light falters. Why this matters extends beyond curiosity. The engine shapes the rhythm of star formation across the disk. When gas clouds near the center are compressed by gravitational tides, they ignite in bursts of creation. When jets and winds from the accretion disk push outward, they regulate that process, preventing runaway collapse. The balance between feeding and feedback determines how galaxies live and age. By studying our own, we learn how similar engines drive the cosmic web at large. It also humbles our sense of place. The sun's orbit is not a perfect circle, but a gentle ellipse that rises and falls above the galactic plane. Each oscillation takes tens of millions of years. Our current position places us on the upward swing, drifting slowly north of the midplane. The stars we call neighbors share this motion, their paths braided together by the common gravity of the disk. Far below, at the center, the black hole and its surrounding mass hold the choreography in place. Without that anchor, the spiral arms would unwind into chaos. There is another layer to this story, the interaction between visible and invisible matter. The dark halo not only holds the stars, but also guides streams of smaller galaxies that fall toward us. These mergers feed the central mass and refresh the disk. Each collision leaves signatures, ripples in velocity fields, arcs of new stars, and trails of stripped gas. The Milky Way's engine, far from being static, is a living mechanism powered by infall and release, tension and resolution. To grasp its complexity, imagine a whirlpool beneath ice. The surface looks calm, But beneath it, water folds in patterns that repeat and evolve. The galaxy behaves the same way. To an observer on Earth, the sky changes slowly, but deep inside the core, orbits twist, jets pulse, and matter cycles in and out. The timescales are immense, yet the processes are continuous. The galaxy is not a sculpture, but a motion that endures. At a human scale, it is difficult to connect with something that vast. Yet the same gravitational logic governs a tossed coin, a satellite, and a star near the center. The difference is only magnitude. Every force we measure, every curvature we plot, echoes that one principal mass tells space how to curve. Space tells mass how to move. The simplicity of that sentence hides the complexity of the world it creates. The Milky Way's engine is the ultimate expression of that dialogue. Our understanding of this structure continues to refine. Infrared observatories now see through the dust, mapping star clusters that orbit close to the core. Radio interferometers trace magnetic filaments extending outward. Each new survey adds another layer of realism to the model. The more we see, the more dynamic the center becomes. It is not a dead weight, but a heartbeat. Its rhythm slow but constant, marking the pulse of our galaxy through time. The greatest revelation is not that there is a black hole at the center, but that the galaxy's shape and longevity depend on it. Without the deep gravitational well, the Milky Way's rotation would disperse over billions of years. The engine does not merely consume, it sustains. It binds together what would otherwise drift apart, a paradox of destruction in service of order. In this sense, the dark heart of the galaxy is also its keeper, so it's standing beneath the night sky. We are unaware of this machinery. The stars look fixed, their patterns serene, yet every glint of light hides motion at speeds beyond imagination, all governed by an invisible core that has been turning since long before the sun was born. To look toward the center is to look into our own origin, because the materials that formed our world were stirred and distributed by this same engine's design. What remains to explore is how this engine transmits its influence outward, sculpting the spiral arms and setting the rhythm for the stars that live within them. The next chapter follows that trail, tracing the architecture of the Milky Way's arms to see how their geometry records the deep pulse of the central power that drives them all. Mapping the galaxy from inside it is like trying to chart the shape of a forest while standing between its trunks. Every direction reveals branches and shadows, but never the whole. For centuries, humanity drew the Milky Way as a mist smeared across the sky, uncertain whether it was a band of light or a crack in heaven. Today, we know it is the cross-section of our own spiral disk, a structure both immense and intricate. Yet even now, defining its full layout demands patience, inference, and faith in data that travel across thousands of light years. The first cartographers of the Milky Way used their eyes as compasses. They measured the density of visible stars, noting where the band brightened or dimmed. Those patterns hinted at arms curling around a central hub, but visible light is fickle, swallowed by dust that fills the galactic plane. The deeper astronomers looked, the less they saw. The galaxy's map remained a silhouette, full of blanks where the dust was thickest. To move forward, they needed a different kind of light, one that could slip through the veil. That light came from hydrogen. The cold gas that fills the galaxy emits radio waves at a wavelength of 21 centimeters, a tone that can cross the dust unhindered. When radio astronomers tuned to this frequency, the Milky Way bloomed in detail. They discovered that the gas was not evenly spread but gathered into lanes and swirls, each marking a spiral arm. The technique was simple in concept yet profound in consequence. By measuring the Doppler shift of the hydrogen line, they could determine how fast the gas was moving toward or away from us. Combine that with our position and a model of rotation, and distance could be inferred. From those inferences came the first true map of the spiral. In plain terms, the galaxy's shape was revealed not by sight, but by sound. The radio tone of hydrogen acted like sonar, bouncing from region to region, letting us reconstruct the unseen corridors of matter. The result was not a flat drawing, but a dynamic chart showing how the arms wind outward from the center in graceful arcs. They are not rigid structures. They are waves of density, compressions that move through the disk like traffic patterns on a circular highway. Stars are born in these waves, live for a while within them, then drift away as the pattern rolls onward. The spiral is an illusion of permanence built from motion. The arms of the Milky Way are labeled with names that sound like directions in a vast city. Sagittarius, Perseus, Scutum Centaurus, Norma, Carina. Each one is a corridor of gas and young stars tracing a different arc. Our sun sits near the edge of a smaller spur, a side street between major lanes, known as the Orion Arm. From this vantage, our night sky is shaped by perspective. When we look along the length of an arm, the star fields appear dense and luminous. When we look outward, across the gaps, the view grows sparse. The bright and dark streaks of the Milky Way's band are geometry made visible. Mapping these arms with precision requires triangulation. Astronomers rely on parallax, the tiny shift in position of a star as Earth orbits the Sun. Nearby stars show a noticeable wiggle, distant ones less so. With modern instruments, even shifts smaller than a millisecond can be detected, corresponding to minute differences in distance. Combined with measurements of velocity from spectral lines, a three-dimensional map of motion emerges. Each point becomes a coordinate in a vast rotating system. The galaxy turns out to be more like a living disk of intertwined rivers than a solid wheel. To put it another way, we are inside a whirlpool and must learn its shape from the traces that pass our way. Radiomasers, natural amplifiers of microwave light found in star-forming regions, act as beacons scattered through the spiral. By observing them with very long baseline interferometry, scientists measure their distances with exquisite accuracy. Each maser pins down a section of an arm, like lanterns along a road. When those lanterns are plotted, the pattern confirms that the galaxy has multiple major arms winding from the center, each separated by broad gaps filled with diffuse gas. The process of mapping is continuous because the galaxy itself evolves. Spiral arms are not fixed lines. They shift as density waves propagate and as gravitational encounters disturb their rhythm. Small satellite galaxies tug at the outer rim, bending and twisting it. Streams of stars pulled from ancient mergers drape across the disk like faded roads. The map, then, is a snapshot of motion, a record of a pattern that refuses to stay still. We measure it not to freeze it, but to understand the currents that sculpt it. Why does this mapping matter? The structure of the spiral tells us how matter flows through the galaxy, how gas collects, and where stars are born. The arms are nurseries, regions where gas is compressed enough to collapse into new suns. Between them lie deserts where the gas is thin and cold. Understanding this pattern explains why the night sky looks as it does and how the ingredients for planets and life are distributed. Our position on the inner edge of a minor spur is not an accident of beauty. It may have been a condition for stability. In the crowded lanes of major arms, supernovae detonate more frequently, flooding nearby worlds with radiation. Here, between the traffic, we orbit in relative peace. Each refinement of the map brings new surprises. Infrared surveys have revealed an elongated bar at the galaxy's core, a central structure that channels gas into the inner regions, feeding both star formation and the supermassive black hole. The bar acts as a gearbox, transferring angular momentum between the arms and the center, maintaining the spiral's rhythm. It is the hidden architecture that keeps the disk balanced, neither collapsing inward nor flying apart. In the interplay between bar and arms, we witness the galaxy's long-term heartbeat. At the outer edge, the disk flares and warps, curving upward on one side and downward on the other. This warp may be caused by tidal interactions with neighboring galaxies or by the uneven pull of the dark matter halo. Whatever the cause, it shows that even structures spanning 100,000 light-years are flexible. The Milky Way is not a rigid wheel, but a responsive membrane floating in gravitational tides. Its warping is slow, measured in millions of years, but it reminds us that no cosmic shape is eternal. To map a spiral is also to confront perspective itself. Every data point we collect depends on the frame we occupy. Our view from within the disk limits what we can see, much as sailors charting an ocean must infer the shape of continents from the behavior of the waves. We rely on calibration against external galaxies, comparing their rotation curves and brightness profiles to ours. The comparison confirms that our spiral is typical among the great disks of the cosmos, neither the largest nor the smallest, neither the most active nor the most quiescent. We inhabit a standard galaxy, yet its details remain intimate mysteries. Imagine flying above the Milky Way and looking down on its luminous arms curling outward like petals. That image, constructed from radio and infrared data, is our collective invention, a way to make sense of invisible motion. It is both real and symbolic. Real, because the measurements support it. Symbolic, because it translates incomprehensible scales into a human vision of symmetry. The act of mapping transforms chaos into narrative. It allows us to say that our home has an address, a structure, a context among billions of others. In this work of cartography, every instrument acts as a sense organ of the species. Optical telescopes gather light from bright clusters. Infrared eyes pierce the dust. Radio arrays listen to the whisper of hydrogen. Together they weave a multi-wavelength fabric of understanding. When the data are aligned, a picture emerges that is as elegant as any myth humanity ever told about the heavens. Unlike myth, however, this picture can be tested. It can be refined, corrected, and expanded as new signals arrive. The map is alive, and so is our relationship with it. At the heart of this mapping effort lies a philosophical question. Can we ever truly know the shape of something we inhabit entirely? The answer may be yes, but only provisionally. Our instruments extend our senses far enough to glimpse patterns beyond direct sight. Yet our interpretation always leans on models and analogies. In that sense, the galaxy we map is also a mirror. It reflects our desire to impose order on motion, to find meaning in the swirl. Each new arm plotted, each gap explained, is a step toward understanding both the universe and the mind that measures it. When we look at the spiral's map spread across a screen, it is tempting to think of it as final. Yet behind every clean line are uncertainties and debates. Are there two major arms or four? Does the bar twist at an angle or run straight through? How far does the disk extend before giving way to the halo? These questions keep the map in motion as surely as gravity moves the stars. Knowledge here is not a destination but a continuous voyage. The better the data, the more subtle the questions become. Our place in this spiral is both ordinary and precious. We orbit a minor star on a quiet lane of a grand structure, moving at speeds we can barely imagine. From here, the arms appear as veils of light and dark across the sky. But in truth, they are the scaffolding of our cosmic neighborhood. To chart them is to define our coordinates in both space and story. The map we draw is a declaration of belonging that we are not at the center, but we are part of the pattern. In the end, cartography of the Milky Way is more than a scientific enterprise. It is an act of orientation in a universe without fixed landmarks. By tracing the arms, we anchor our imagination to something larger than our individual worlds. We transform drifting data into a sense of home. The spiral becomes not just an object of study, but a compass rose in the endless ocean of the cosmos. The next stage of this journey will follow the flow of stars and gas as they move through these mapped corridors, converging toward the meeting point where galaxies approach each other and tides of gravity begin to shape new horizons. Every orbit carries with it a promise of return and a risk of collision. The Milky Way, immense though it is, moves within a crowded neighborhood. Across the cosmic gulf, another spiral galaxy drifts toward us, its glow faint but insistent. That galaxy is Andromeda. a distant sibling roughly twice the size of our own, and its motion through the void ensures that one day, the two will meet. The coming encounter is not a guess, but a measurable trajectory, a story written in the language of light and velocity. From Earth, Andromeda appears as a small smudge in the constellation that bears its name. To the unaided eye, it looks still, serene, eternal. But long exposure photographs and spectroscopic measurements reveal a different truth. The entire galaxy is moving toward us at about 110 kilometers per second. That approach, first detected by the subtle blue shift of its starlight, has been confirmed by countless observations. For decades, astronomers wondered whether this motion was a temporary fluctuation or a true path toward collision. Then data from space telescopes resolved the uncertainty. Andromeda is not sliding past, it is inbound, bound by gravity, and on a course that will unite the two galaxies roughly 4 billion years from now. The scale of this event is hard to imagine. Each galaxy spans over 100,000 light-years, and yet the space between their stars is so vast that direct collisions between suns will be rare. When galaxies collide, the drama unfolds not in impacts of solid matter but in tides of gravity. Stars shift their orbits, clouds of gas compress, and the shape of each system is pulled into new forms. From a distance, it will resemble two luminous whirlpools drawing together, their arms stretching and merging like threads of smoke. At the center of each, the supermassive black holes will spiral inward, eventually coalescing into a single, even more massive heart. In plain terms, the galaxies will not crash like stones, they will merge like clouds. The gravitational attraction between them will distort both structures long before their centers meet. Tidal bridges of stars will arc across the dark between, and streams of debris will fan out into intergalactic space. Over millions of years, these streams will settle into loops and shells, relics of the encounter visible for eons to come. Our Sun and its planets, carried within one of the Milky Way's spiral arms, will follow the larger flow, likely surviving the merger but emerging in a very different night sky. It may seem strange that two galaxies can meet at all in a universe that is expanding. After all, most galaxies move away from each other as the fabric of space stretches. The explanation lies in local gravity, within the small cluster of which the Milky Way and Andromeda are members. Gravity overpowers expansion. The galaxies are close enough, only about 2.5 million light-years apart, for their mutual pull to dominate. The expansion of space between them is weaker than the attraction drawing them together. Thus, while the wider universe races apart, our corner converges. To watch this approach unfold is to glimpse the geometry of inevitability. Andromeda's motion is not chaotic but calculated, governed by the same equations that describe an apple falling to Earth. The difference is one of scale and patience. Over billions of years, small accelerations accumulate into decisive shifts. The encounter is a slow choreography that has already begun. The space between the two galaxies is not empty. It is threaded with diffuse gas that feels the pull long before the stars do. Observations of that gas reveal streams already forming, a prelude to the merger's grand finale. Why does this matter to us? Creatures bound to a single planet with a fleeting lifespan. It matters because encounters like this define the growth of galaxies. Collisions and mergers are how the universe recycles its structure. Each meeting reshapes the distribution of matter, ignites new waves of star formation, and builds the next generation of cosmic architecture. The Milky Way itself is the product of such mergers, having absorbed smaller galaxies over billions of years. What lies ahead is not an anomaly, but a continuation of that process. The next verse in an ancient rhythm. Picture the future sky. As the galaxies draw near, Andromeda will swell from a faint blur to a dominant feature. Its spiral arms will become visible to the naked eye, spanning a field larger than the full moon. Over millions of years, it will fill the night, first as a glowing arc, then as a sky of interwoven stars. When the two galaxies finally overlap, the heavens will blaze with new star birth triggered by compressed gas clouds. Nebulae will light up like fresh constellations. to any life that endures through those epochs. The universe will seem newly alive. There will be turbulence as well. Gravitational tides may fling some stars into long, looping trajectories far from the merged core. Others may find themselves on altered orbits, trading neighborhoods as the new galaxy takes shape. Our own sun, depending on its phase in stellar evolution, may be carried to a more distant orbit or even expelled to the outskirts. Yet despite this chaos, space will remain mostly empty. The distances between stars are vast enough that direct collisions are unlikely. The violence of a galactic merger is an art of gravity, not of impact. In everyday language, what will happen is a blending, not a breaking. Two disks of light will swirl, tear, and reassemble into one. Astronomers have simulated this process using computers, watching as countless points of data mimic stars. The result is both scientific and poetic. The merged galaxy, often dubbed Milkomeda, will likely become a massive elliptical, smoother and rounder than the spirals that formed it. Its new core will host a central black hole of combined mass, surrounded by a halo of stars that once belonged to separate cities of light. Such encounters leave deep imprints. The energy released when the central black holes merge will send ripples through space-time, gravitational waves that echo across millions of light years. Even before that, the movement of gas will feed bright quasar-like activity, shining as the new core stabilizes. Long after the spectacle fades, the structure that remains will continue to evolve, slowly cooling into a quieter form. The Milky Way and Andromeda will no longer exist as distinct entities. They will be a single organism, the product of cosmic fusion. From a human perspective, this knowledge is both humbling and liberating. It reminds us that permanence is an illusion on every scale. What we call home is transient, its form temporary in the long flow of time. The patterns of stars that guided our ancestors are destined to dissolve. Yet the same laws that guarantee their dissolution also ensure continuity. The matter that makes us, the atoms of our world, will remain part of the greater galaxy that emerges. The encounter does not end the story. It transforms it. Think of the galaxies as dancers in an endless waltz, drawn together by the same rhythm that keeps planets circling stars. The tempo is slow beyond imagination, but the steps are precise. Each swirl brings the partners closer until they move as one. The Milky Way's spiral arms, now mapped and measured, will become ribbons in this dance, stretching and blending into new patterns. Our cartography of the present becomes the choreography of the future. Why it matters once more studying this encounter gives us a model for cosmic destiny. What we see in Andromeda's approach echoes throughout the universe. Mergers are how structure evolves, how diversity arises from simplicity. The Milky Way and Andromeda are not exceptions, but participants in the universe's grand experiment of change. By observing their motion today, we witness the slow pulse of creation operating on scales too vast for the heart to grasp, yet entirely within the reach of mathematics. There is a subtle comfort in knowing the outcome. The collision will not happen in our lifetimes, nor in the lifespan of our species. Yet it will happen. The future sky already exists in the data. Every spectral line and parallax measurement contributes a thread to that tapestry. To gaze at Andromeda tonight is to look at an event still billions of years away but already decided. In that sense, the light we see is both history and prophecy. The encounter also ties us to other galaxies across the cosmos. Everywhere we look, pairs and groups of galaxies show the same pattern of attraction and merger. These events create the giant ellipticals that dominate the centers of clusters. Each is a monument to gravitational inevitability, built from countless smaller unions. The fate of the Milky Way is a local version of a universal theme. In studying it, we read the script of the cosmos itself. Our understanding of this future does not rely on speculation alone. It is grounded in measurement, the drift of spectral lines, the tangential motion of stars, the patterns of gas mapped in ultraviolet and radio. Each new instrument refines the prediction. Gaia's precise tracking of Andromeda's stars confirms that the approach is direct. Hubble's earlier data already hinted at it. The consensus grows with every observation. The two spirals are bound, and their meeting is certain. As the vision becomes clearer, a final question emerges. What will the new galaxy mean for whatever consciousness endures to witness it? Will life find a way to look up and marvel? Or will the spectacle unfold in silence? The universe will not wait for an audience. It performs regardless. Yet the act of knowing, of measuring the approach and imagining its outcome, connects us to that performance. We become participants through awareness, drawing meaning from motion itself. The sky that follows the encounter will be unrecognizable, a dome filled with overlapping stars and new constellations. The Milky Way's familiar river of light will dissolve into a glowing oval, brighter but less distinct. Within that new system, the merged core will shine, surrounded by long trails of orphaned clusters. In that glow, the memory of two separate galaxies will live on, woven into one grand structure. The story of the coming encounter is not a warning, but a revelation of continuity. Matter does not end. It changes arrangement. The stars do not vanish. They migrate into new orbits. The Great Collision is the universe expressing its rhythm of renewal. To watch it approach, even through equations, is to glimpse the future written in the language of gravity. Our next chapter will follow the rivers that extend beyond these merging spirals, tracing the larger flows of clusters and voids that define the motion of entire superclusters, where attraction and absence together steer the fate of all visible matter. From the outside, galaxies look solitary, adrift in blackness. Yet each one belongs to a greater current, a river of gravity that pulls and guides it through the cosmic landscape. Our Milky Way is no exception. Though it spins as if self-contained, it moves as part of a much larger flow that stretches across hundreds of millions of light years. This flow belongs to a vast domain known as Laniakea, the immense supercluster that gathers thousands of galaxies into one gravitational basin. To understand our true direction, we must trace these invisible rivers that run through it. Laniakea means immense heaven, and the name suits its scale. It encompasses the Milky Way, Andromeda, and tens of thousands of other galaxies bound together not by physical walls but by shared motion. Think of it as a continental divide written in gravity instead of terrain. Each galaxy within it falls toward the same basin, flowing along paths determined by the distribution of mass and voids. The boundaries are not drawn by density, but by direction. Where the flows diverge, one supercluster ends and another begins. Astronomers discovered Laniakea by mapping galaxy velocities in 3 dimensions. They measured not only where galaxies sit on the sky, but also how they move relative to one another. When the data were plotted, a pattern emerged. Vast regions of space were sliding toward a common attractor, a region of greater density that acts like a gravitational sink. At the same time, other areas drifted away from a neighboring void, a bubble of near emptiness that repels through absence. Together, these two forces, pull and release, define the streams that shape our cosmic geography. In everyday language, imagine drops of water flowing down a valley. Some run toward a deep lake, others slide away from a hilltop. In space, gravity provides the slopes and hollows. The galaxies are the drops, their velocities tracing the shape of the unseen terrain. Our local group, containing the Milky Way and Andromeda, is one of many such drops following the gravitational gradient toward a basin known as the Great Attractor. Around that destination, the flow lines converge from every direction, threading together into a network of streams. It is through this network that our galaxy travels. To map these cosmic rivers, scientists rely on surveys that record both distance and velocity. The distance is measured using standard candles such as supernovae or Cepheid variable stars, whose intrinsic brightness is known. The velocity comes from redshifts and blue shifts, the stretching and squeezing of light due to motion. When combined, These measurements form a velocity field, a kind of topographic map where contours represent equal motion. The result resembles a fluid simulation on a cosmic scale, with galaxies drifting like plankton in invisible tides. What this map reveals is both elegant and humbling. The Milky Way does not move randomly through space. It glides along a filament, a gravitational corridor connecting clusters and groups. The flow passes near several notable features: the Virgo cluster, the Hydra Centaurus region, and the Norma cluster, which marks the heart of the Great Attractor. Our journey takes us along this filament, toward the center of Laniakea's gravitational basin. Beyond it, the currents turn again, feeding into even larger structures that continue outward to the edge of the observable universe. The Great Attractor is not a single object, but a dense region of galaxies and dark matter. Its mass is so large that it bends the paths of everything nearby, even light. Yet the attractor itself remains partially hidden behind the plane of our galaxy, obscured by dust and stars. Radio and X-ray observations pierce this barrier, revealing clusters of galaxies piled together like stones in a dam. Their combined gravity defines one of the most powerful concentrations of matter in our local universe. The Milky Way's motion toward it, at several hundred kilometers per second, is a testament to its influence. Opposite the attractor lies a vast void, an underdense region that exerts a different kind of force. Where mass pulls, voids push, not by active repulsion, but by the absence of counterbalancing gravity. The void behind our galaxy allows the flow to accelerate toward denser regions ahead. The balance between attraction and emptiness sculpts the cosmic landscape into filaments, sheets, and hollows. In this architecture, we are a small part of an immense web, drifting between the push of nothing and the pull of everything. At its core, the study of Laniakea transforms how we picture the universe. For much of history, humanity saw the cosmos as a collection of isolated islands. Now we see it as an interconnected system where structure arises from motion. Galaxies are not merely static lights. They are participants in a cosmic circulation. The supercluster itself is a watershed, with currents converging towards central basins. The analogy is more than poetic. It defines boundaries that can be mapped, much as we map river systems on Earth. Simply put, Laniakea is our cosmic continent, and the Great Attractor is its gravitational ocean. Everything within its boundaries flows toward that central depth. Beyond its edge lies another continent, Perseus Pisces, whose galaxies follow different slopes. Between them stretches a ridge of slower motion, the cosmic divide that separates their domains. These divisions are not physical walls, but differences in velocity vectors, invisible fences drawn by the way space itself is bending. Why it matters can be felt in perspective. Knowing that the Milky Way belongs to a larger flow reframes our sense of motion. We are not drifting alone through a random void. We are part of a coordinated migration, a journey written into the structure of the universe. The rivers of Laniakea are evidence of coherence across unimaginable distances. They remind us that gravity is not just a local force, but a universal storyteller, shaping the paths of galaxies as surely as it shapes the fall of an apple. Each measurement of this flow refines our understanding of cosmic structure. Surveys using radio telescopes, infrared detectors, and spaceborne observatories have filled in the map over decades. They reveal a lattice of filaments connecting clusters, and within that lattice, smaller streams leading to local basins. The Milky Way's motion combines several components: the rotation around its own center, the drift toward Andromeda, and the shared plunge toward the Great Attractor. Subtract one layer after another, and what remains is our true vector through Laniakea's network. Some scientists describe this as the cosmic velocity web. In this web, nodes correspond to dense clusters, filaments to the channels between them, and voids to the empty cells that give the pattern its shape. The arrangement resembles a three-dimensional foam, frozen in slow motion. Yet it is not static. Over billions of years, the nodes grow by pulling matter along the filaments, while the voids expand as they empty out. The web is both architecture and process, structure and story unfolding together. Think of it like this. The Milky Way is a leaf floating down an invisible river. The currents that carry it are shaped by ridges and hollows in the gravitational field. Other leaves, other galaxies, float beside us, their paths converging as they approach the same basin. If we could trace their motions backward in time, we would find that many diverged from common points, remnants of earlier flows. The entire history of cosmic structure is written in these trajectories. By reading them, we reconstruct not just where we are going, but how the universe built itself. At human scale, the numbers are staggering. The Laniakea supercluster spans about 500 million light-years. Light from its farthest edges has been traveling since before complex life appeared on Earth. Yet the pattern of motion that defines it is measurable through careful observation. The coherence of those motions, revealed through redshift surveys, confirms that gravity sculpts structure far beyond the scale of single galaxies. The universe, it seems, organizes itself into patterns that echo across all magnitudes. The realization that we are part of Laniakea changes our sense of orientation. It replaces isolation with connection. When we look up at the night sky, the stars appear scattered, but they are markers in a flow. Even the smallest telescope captures light that participates in the same journey. Our solar system's course, measured against the background radiation, includes this component of collective motion. The direction is set not by local whims, but by the large-scale geometry of matter and void. As the mapping of these flows grows more precise, another insight emerges. The Great Attractor, massive though it is, may itself be only a feature within a still larger structure. Beyond Laniakea lies an even greater region, sometimes called the Shapley supercluster, toward which parts of Laniakea's matter may also drift. The hierarchy continues outward, like rivers joining rivers into ever broader basins. The picture that emerges is one of cascading motion, from galaxies to clusters to superclusters, each nested within the next. Why it matters, once again, understanding these flows is the key to deciphering cosmic evolution. The distribution of mass, both visible and dark, sets the stage for everything that follows. By tracing the rivers of Laniakea, we learn how the early universe's fluctuations grew into the structures we see today. We also glimpse our future, since the same flows that draw galaxies together now will one day determine their final configurations as expansion accelerates. If one listens carefully, the idea carries a deeper resonance. The universe is not a frozen sculpture, but a living current. Matter moves, expands, and converges, creating forms that persist for a time and then give way. Laniakea is a snapshot of that motion, a portrait of gravity at work on the grandest scale. Our maps are still crude, our distances uncertain. Yet each new observation adds another brushstroke to the canvas. The rivers become clearer, the basins more defined. We find meaning in that clarity. To locate ourselves within Laniakea is to accept that our home galaxy is part of a much greater design. The name Immense Heaven is not just poetry. It is a statement of belonging. We are droplets in an ocean of galaxies, moving according to laws that are both simple and profound. Our task is to follow those laws with attention, to measure the flows, and to understand how attraction and emptiness together shape the destiny of the visible world. The next chapter will turn from these vast rivers to the contrast that defines them, the tension between pull and void, between mass that gathers and space that yields, revealing how gravity and absence together write the story of the cosmos. Every river needs a source and a gradient, and the universe is no different. The grand flows through Laniakea, the gentle drift of our galaxy, the acceleration of clusters across the cosmic map. All owe their form to two opposing features: regions of mass that attract, and regions of emptiness that appear to push. The dance between pull and void sculpts the universe as surely as gravity sculpts the path of a falling stone. Yet here, the stone and the well are made of galaxies, and the falling happens across hundreds of millions of years. The first hints of this cosmic polarity came from patterns in motion. When astronomers plotted the peculiar velocities of galaxies, the deviations from the general expansion of space, they found direction. Many galaxies, including our own, moved toward a dense region known as the Great Attractor. But the flow was not symmetrical. Opposite the attractor lies a vast underdense region, the dipole repeller, a cosmic cavity almost devoid of galaxies. The combined effect of these two structures explains our motion through the universe far better than attraction alone. It is not just gravity that pulls. Emptiness itself creates a kind of release, an absence that allows motion to accelerate. In everyday language, think of space as a landscape of hills and valleys drawn by mass. A valley of dense galaxies pulls matter downhill. A hill of low density lets matter roll away. The Milky Way and its companions are caught between these two contours, sliding along the gravitational slope shaped by both. What we call the pull and the void are not opposing forces in the normal sense, but complementary expressions of curvature in the fabric of space. To make sense of this, imagine two kinds of cosmic terrain. In the first, clusters of galaxies form peaks of gravity, places where the local curvature is deep and steep. In the second, voids expand, their sparse contents drifting outward as if repelled by the surrounding mass. The interplay between these terrains forms the large-scale structure we observe, filaments stretching between clusters, sheets of galaxies outlining voids, and the empty bubbles in between, where attraction gathers, light and matter collect, where emptiness rules, expansion dominates. The universe grows not from one principle, but from the balance between presence and absence. Our position in this architecture is strategic. The Milky Way's motion toward the Great Attractor and away from the dipole repeller defines the local flow that places us within the Laniakea basin. The speed of this motion, about 600 kilometers per second relative to the cosmic background, has been measured through the dipole anisotropy in that background radiation. The pattern is a subtle tilt in the temperature of the microwave sky, slightly warmer in the direction we move, slightly cooler behind us. That tiny difference, only a few thousandths of a degree, encodes the motion of everything we know toward the region of greatest mass and away from the region of greatest emptiness. The discovery of voids changed the way we see the universe. Early cosmological maps assumed galaxies filled space fairly evenly. As the data improved, large-scale surveys revealed something startling. Most of the universe is empty. Galaxies cluster along thin walls and filaments, leaving vast cavities between them. These voids, often tens or even hundreds of millions of light-years across, contain only a few lonely galaxies or clouds of gas. They are not truly vacuums, but compared with the surrounding filaments, they might as well be. Their presence ensures that gravity's work is never uniform. Where matter is sparse, expansion proceeds faster, pushing galaxies apart more efficiently than in denser regions. Simply put, the voids are the universe's exhalations. They are where space breathes outward, giving shape to everything that remains. Without them, clusters would never separate into the distinct forms we observe. The empty regions act as gravitational counterweights, stabilizing the growth of structure. As they expand, they drive matter toward the denser filaments, sharpening the contrast between light and dark. The cosmic web, in its delicate tracery, is the result of billions of years of this push and pull. Why this matters is clear when we consider our own motion. The Great Attractor alone cannot account for the full vector of our drift. Only by including the dipole repeller does the model match observation. We move not only because something pulls us, but also because something else lets us go. This dual influence refines our map of local space, turning what once seemed a single attraction into a balanced dynamic between density and void. The interplay is so precise that removing either from the calculation breaks the coherence of the flow. At human scale, the idea that absence can shape motion feels abstract, but its consequences are visible everywhere. Consider a sailboat. The wind moves from regions of high pressure to low, and the boat rides that difference. In the universe, mass is the pressure, and voids are the low zones. Matter drifts along the gradients created between them. In this sense, the cosmos is a vast sailing field, with galaxies as vessels carried by the invisible wind of geometry. The existence of voids also carries implications for the fate of the universe. As cosmic expansion continues to accelerate, driven by dark energy, the voids will dominate more and more of space. Over billions of years, the filaments will thin, clusters will drift apart, and the visible universe will fragment into isolated islands. The great rivers of motion we map today will dry into stillness, each supercluster surrounded by expanding emptiness. The pull of mass will remain, but it will no longer overcome the push of expansion. The current epoch, with its balance of void and structure, is a fleeting equilibrium in cosmic time. Think of the void as a mirror that reflects the power of gravity by its absence. Just as a sculptor reveals form through the space between shapes, the universe reveals its architecture through the gaps between galaxies. The larger the voids grow, the more pronounced the remaining structures become. Their expansion is not destruction, but definition. By receding, they make the filaments stand out in sharper relief. The cosmic web is thus both a creation of matter and a signature of emptiness. Our instruments have begun to map these voids with remarkable detail. Redshift surveys such as the Sloan Digital Sky Survey chart the distribution of galaxies across billions of light-years, showing the bubble-like pattern of matter and emptiness. Computer simulations, seeded with the physics of gravity and dark energy, reproduce this pattern with astonishing fidelity. The agreement between observation and theory confirms that voids are not anomalies. They are fundamental to how the universe evolves. They occupy most of its volume, silently orchestrating the motion of the visible few percent that glows. At its core, the relationship between pull and void is a study of balance. Gravity gathers, expansion disperses, density contracts, emptiness inflates. The universe grows by allowing both to coexist. The Milky Way's current path is evidence of that balance. We are drawn inward toward mass while simultaneously lifted outward by the surrounding void. This state will not last forever. As expansion accelerates, the void's influence will increase, and the great attractors of today will eventually lose their grip. What remains will be islands of matter adrift in a vast, cold sea of dark energy. In simple terms, the universe is like a tide pool at the edge of a retreating ocean. The water recedes, leaving behind clusters of life surrounded by widening gaps. The tide itself is dark energy, and the pools are the superclusters. Over unimaginable time, the gaps will widen until even the nearest pools can no longer exchange signals. The cosmic web will dissolve into solitude. Yet even then, the memory of motion will persist, written in the leftover velocity of galaxies frozen at the limit of observation. Why it matters once more, this understanding turns the concept of nothing into something measurable. Emptiness is not a void in meaning, it is a player in the cosmic drama. By shaping how matter moves, it gives the universe texture and direction. To map the pull without acknowledging the void would be like studying wind without pressure or sound without silence. The universe is a conversation between presence and absence, each defining the other. As we trace these patterns, we also trace our own lineage within them. Every atom in our bodies once belonged to regions of density that condensed under gravity's pull. While the space around us expands into the growing void, we are products of both. Our existence depends on attraction, yet our future unfolds in expansion. Between those forces, life wants its fragile balance. The night sky is a record of that balance, a freeze frame of the moment when the pull still contends with the void. Somewhere beyond the Great Attractor lies the edge of our influence, the point where the void's expansion wins completely. Beyond that horizon, light from distant galaxies will fade as the universe's growth stretches it beyond detection. In that far future, observers will see only their own local cluster, unaware that others ever existed. the cosmic web will have vanished, leaving no map but memory. But we live in the time of flow, when rivers still run and voids still breathe. The pull and the void together write the motion that defines our place in space. To understand them is to glimpse both origin and destiny, the compression that began the universe and the expansion that will finish it. The equilibrium between these forces is fleeting, but within it lies everything we know. It is the fragile pause between gathering and dispersal, between the making of galaxies and the quiet that will follow. The next act will step beyond maps and measurements to ask what such a universe means for consciousness, purpose, and time itself. When the rivers dry and the stars go dark, yet the story of motion still echoes in memory. The story of motion has led us outward from our own stillness into the great flow that carries galaxies, clusters, and superclusters across the expanding sea of space. Now it brings us inward again, toward the question that hovers behind every measurement. What does motion mean when the traveler, the path, and the destination all belong to the same fabric? The universe does not drift through something larger. It moves within itself, changing shape while remaining whole. For those of us who can think about that motion, who can measure and describe it, there is a responsibility that feels almost sacred. To witness is to participate. We have learned that there is no final frame of rest, no fixed origin to claim as home. Every coordinate we draw floats upon another. Every orbit depends on another orbit. The heart of the Milky Way anchors us to a center that itself is moving. The supercluster defines a basin that itself is sliding along a deeper gradient. The push of the void and the pull of mass balance each other only for a moment. Yet in this endless recession of frames, awareness itself becomes a kind of anchor. The act of knowing creates a point of reference that no external motion can erase. Think of the night sky as both map and mirror. Every star we see is a traveler, its light stretched by motion, its history entwined with ours. The photons that reach us tonight left their homes before humanity existed, before even the continents took their current shape. By receiving them, we inherit their journey. Observation makes us part of the continuity they describe. The telescope is not just an eye. It is a bridge across time, a way for the universe to notice its own behavior. In everyday language, we could say that knowing the universe moves is knowing that change is the normal state of being. The galaxies swirl. The stars are born and die. The very atoms in our blood were forged in long-dead suns. Stability, so precious to our daily lives, is only a small-scale illusion. Yet within that illusion, we find the space to think, to create, to ask why it should matter that everything moves. Perhaps meaning itself arises from the temporary harmony between order and drift. The study of the cosmos teaches patience. To see one cycle of a galaxy's orbit would take hundreds of millions of years, but we can trace it through the accumulation of data and imagination. That act of extrapolation is a human echo of cosmic process. We cannot wait for the dance to unfold, so we reconstruct it in thought, turning fragments of evidence into a continuous motion of understanding. Knowledge becomes its own form of time travel, a way of touching scales we will never live to witness. At a deeper level, our pursuit of cosmic motion is a pursuit of coherence. We want the universe to make sense, to form a pattern our minds can hold. When we map its rivers and measure its pulls, we create a geometry of belonging. The equations do not merely describe, they invite participation. To calculate an orbit is to admit we are also part of that orbit. To speak of dark matter and voids is to confess that absence and uncertainty live within us as well. Why this matters returns again and again to perspective. In a cosmos where no position is privileged, the observer becomes significant not by location, but by awareness. Our ability to measure and to wonder is the universe folding back upon itself, testing its own reflection. Each act of observation completes a loop of existence matter organizing into mind, mind turning to measure matter, the circle closing and beginning again. The realization does not diminish us, it situates us inside the pattern we sought to describe. The future we have glimpsed is not one of destruction, but of transformation. As galaxies merge and the voids expand, the universe continues its experiment in change. Stars will fade, elements will scatter, but structure will remain, even if it exists only as faint radiation spread thin across eternity. To call that ending is a mistake. It is a continuation by other means, a transition from visible order to hidden equilibrium. Energy will still flow, and perhaps somewhere, consciousness will adapt to that new scale of quiet. There is poetry in the way the universe hides its permanence within impermanence. The same laws that guarantee decay also guarantee consistency. Gravity still binds. Light still travels. Entropy still writes the direction of time. These laws are the script of reality. Indifferent, yet reliable. They form the foundation upon which life builds its transient moments of beauty and meaning. If the cosmos were truly chaotic, thought could never arise. The fact that we can speak of order at all is proof that order exists deeply enough to sustain reflection. In this light, the void no longer seems like a threat. It is the necessary silence that allows the music of motion to be heard. The spaces between galaxies give rhythm to the clusters, just as pauses give shape to words. Without emptiness, there would be no form. Without form, there would be no awareness. The same emptiness that will one day isolate our descendants is also what made their existence possible. The void gives context to presence, and presence gives meaning to the void. Our understanding of time must change as well. We think of it as a river flowing from past to future, yet in cosmic terms, time is also a dimension of structure. When we observe distant galaxies, we are looking backward, but we are also looking outward. Space and time are threads of the same fabric, and motion is the weaving that binds them. The expansion of the universe is not an explosion into emptiness, but a deepening of this fabric, a creation of room for new relationships to form. Each moment is both a location and an event. At human scale, the vastness can feel alien. What is the value of our small lives against the backdrop of superclusters and cosmic voids? The answer lies not in magnitude, but in participation. Conscious beings are the way the universe becomes aware of itself. When we study the sky, we fulfill one of its potentialities. Our curiosity, fragile and finite though it is, transforms immensity into intimacy. Every measurement, every thought, is an active connection between the part and the whole. Consider again the image of the Milky Way arching across a dark horizon. That light is the collective memory of billions of suns, each burning for its own brief time. Our species arrived late to this spectacle, but we carry the ability to understand it. The photons that fall into our eyes complete journeys that began before the Earth existed, and in catching them, we extend their story. The act of seeing is an act of joining, the simplest form of cosmic communion. In plain terms, the universe is a conversation, and we are both listener and reply. The stars speak in light, and we answer in thought. The dialogue has no beginning and no final word. It unfolds as long as there are minds to interpret it, instruments to extend those minds, and matter to sustain the cycle. To be aware of this conversation is to realize that meaning is not a property of the universe alone, but of the relationship between observer and observed. Why it matters once more, our knowledge of motion does not diminish wonder. It refines it. Understanding that the stars move does not make them less beautiful. Knowing that galaxies will merge does not make them less miraculous. Science and awe are not opposites, but partners. One gives detail, the other gives depth. Together, they let us inhabit a universe that is both measurable and mysterious. As we look ahead, the picture grows quieter. The distant galaxies will fade beyond our horizon as expansion quickens. The sky will lose its depth, and the cosmic web will thin until only local clusters remain. But meaning will not vanish with the light. It will reside in the memory of understanding, in the patterns recorded, and the thoughts passed forward. even if the cosmos ends in cold stillness. The knowledge that it once moved and that we once measured its motion is itself a form of permanence. It is tempting to call this future bleak, yet perhaps it is serene. The universe does not mourn its transformations. It simply continues. Stars fade, atoms disperse, but the laws that govern them endure. In that endurance lies a kind of quiet grace. We are made from impermanent matter obeying permanent rules, and through us, those rules gain voice. To know this is to find peace in change, a sense of belonging even to endings. What, then, remains for us? Beings of fleeting consciousness, in a universe destined for slow silence. The answer may be as simple as this: to observe, to understand, and to remember, to let knowledge become empathy, turning the cold geometry of space into a shared story. We cannot halt the drift, but we can trace it. We cannot stop time, but we can make it meaningful. The last light of distant galaxies will one day fade into the background, leaving only the whisper of expansion and the memory of structure. In that future silence, if awareness endures somewhere, it will still ask the question that echoes through every age when the universe forgets its own motion: who will remember it?